Hi, welcome to all of you. And this is the beginning of our a new chapter, which is called complex numbers. Now, complex number it was a controversial subject. The imaginary numbers, the name imaginary was a derogatory name, which was a great mathematician, Rene, who coined it. And but later on, one of the greatest mathematician of all time, Euler. You must have heard Euler's identity. We'll study that. Day and Cauchy, right? And this is extremely useful in the engineering branch and in the computer science branch. So a complex number is made up of two parts. One is the real number. I'm sure you are all aware of the set of real numbers. Every number of the real line is real number. And the imaginary number. The imaginary number is defined in such a manner that I squared is equal to -1. Now we'll see what it does. Okay. Now, if someone says, no, I need I to the 3, so you could write I squared into I. So I squared is -1, which will be minus I. And it can go on and on and on. Right. So a complex number is of the form A plus B to the I. Remember, A and B are real. And this becomes imaginary because of the presence of I. Why do we need this I? So, for example, obviously there could be a quadratic or any polynomial of this kind. Now, how do you evaluate it? How do you get square root is something? Suppose, for example, x squared is equal to 25. So there exist two numbers, 5 and -5, which when multiplied with itself gives 25. There's no number which does that. So therefore, the uh, imaginary number were born. Now there are certain properties to it. There are there's a huge amount of material available on this, but I don't think so. That's very relevant as of now. I'm just going to scrape through everything, right? So first is the property of closure, which says that there's a set of complex number, and you take two complex numbers, do some operation on it like subtraction, addition, multiplication, the result will be a complex number. Associativity means the order of addition will not matter. There are three numbers A, B, C. You add A plus B and then C, or you add A plus C then B. It will not matter. Then commutative, in addition, it doesn't matter whether you add 3 to 4, 4 to 3. Similarly is the case with the complex number. This is important. There's something called additive identity. Now, additive identity is defined in such a manner that it gives the number itself. So, suppose A plus BI, right? And I can add something called 0 plus 0i, right? So, this is called an additive identity that when this is added to this, I'll get the number, right? I get an additive inverse like that. So additive inverse is defined as, let's say, A plus BI, and there's some number which is additive inverse. So it has to be, K has to be like that, that when these two are added, I should get 0 plus 0i. Right? For example, in real number case, A plus minus A is the additive inverse of A. Just remember this. Again, we are not studying real analysis or not getting into details. Same is the case with subtraction in case two numbers are subtracted. So suppose the numbers are 4 plus 3i and you want to subtract 2 plus 6i. Please remember, subtract real from real part, imaginary from imaginary part. So it should be 4 minus 2 plus 3 minus 6 to the I. So whatever number will be formed will be a complex number, right? Uh, it is the closure property I've discussed that it will be a complex number. Now, I'm sure you must have seen this, that A minus B is not equal to B minus A, right? It can't be. Again, A plus B plus C is not equal to A plus B plus C, right? In the case of complex numbers. Then we have multiplication. So again, you have to multiply two complex numbers. That's something which is extremely, extremely easy. I could just show you to you how to do it. Suppose 4 plus 3i has to be multiplied to 2 plus 6i, anything, any number. So the basic rules of algebra, you multiply 4 by 2 is by 6, 3 by 2, 3 by 6. You get 4 to the 8 plus 4 6 are 24 times I plus 3 to the 6 times I plus 18 I squared. This will become minus 1 multiplied by 18. This will become 8. These two will become the real part, and these two, when added, will give you the imaginary part. It's the commutativity A into B is B into A, B, C is equal to B, A, C, or whatever. Yes, there's something called multiplicative identity. So, multiplicative identity is something which is like when you multiply it, it gives you the same number. How is it helpful? I'll just take a number A. Multiply it with 1, you get A, right? So, I call it 1 as the multiplicative identity, correct? And the what is the advantage? We'll see. There's something called multiplicative inverse. So multiplicative identity for A is 1 and multiplicative inverse is 1 by A. So A, when multiplied by its multiplicative inverse, gets 1. Again, please don't get bogged down with these. These are simple. This is very simple stuff, just made complicated by writing so many. Uh, we are not analyzing or trying to see the origin of it. Division. So we will do division. It's like A plus BI divided by C plus DI, right? Just remember while dividing that C plus DI in the denominator, we never ever have a imaginary part. So what we can do is we can rationalize it by something called conjugate. This gets cancelled now. So what happens is when these two are multiplied, I get a real number downstairs. Upstairs, I have a complex number, and overall, it will be a complex number. So, for example, I want to multiply 3 plus 4i, divide by 2 plus 3i. I'll take a number which we call conjugate. So the conjugate is 2 minus 3i upon 2 minus 3i. It's, you remember, rationalization. So when these two are multiplied, this is nothing but a plus b into a minus b, which will be whatever this number will be. It will be a squared minus b squared. So it will be 2 squared minus 9i squared. I squared is minus 1. So this will be plus, and this will become a real number. The important part is the representation of the complex number. Representation of a complex number, which is called Argand-plane. It doesn't matter what it is called. You need to know how it is represented. So, since complex number is of this type, z is equal to x plus y, I or iy. This is real, and this is and this entire thing is imaginary, and this is iota. So what we do here is this is a coordinate system. This is real and this is imaginary. So any number, for example, 3 plus 4i, can be represented as we go 3 units here. Units means meter, centimeter, that's up to you, and 4 units here. And then we see that this point, let's say this point is P. This point is this particular number on this plane. And how far is this number from origin? I can draw a line and see that this number is this far. All right. Okay. Now, this is 3 and this is 4. So this is going to be 5. I'll just draw a line to be more, precise here. So this 5 number will be called modulus of the complex number, and it is denoted by mod of z. Then there is this angle. This angle is called the argument, AR. How can I calculate the argument? Simple. In this triangle, you can take tan theta, which is 4 by 3, and theta is equal to tan inverse 4 by 3. So you have the argument, you have the modulus as well as the argument. But then it's not that simple. There are two cases I want to discuss where the representation will have a different connotation. So, for example, there is a number which is simple, 1 plus I. Real part, imaginary part. No problem. I draw, and this is the positive part, this is the negative part, this is 1, and this is the number. And I, again, the same stuff. This is 1, this is 1. Now, this will be root 2. Remember, this number is 1 plus I, and this angle is theta. So the modulus is root 2, and theta is equal to 10 inverse 1, which is pi by 4, not an issue. Now, let me change this. Suppose the number is 1 plus I, a negative sign here. So the real part is negative. Now, this is not this number. For this number, I have to go here, right? And here. So this is 1, and this is the point. So the number would be somewhere here, all right? This is the number -1 plus I. All good. I want to calculate the modulus, which will be root 2. Not a problem. I can calculate this angle, which is what? Now, this is a problem, that this angle is what? And this is not the angle that I'm looking at. The angle between the complex number and the positive direction of x-axis. Please remember, I'm interested in this angle, this one, and not this angle. So what I'll get, suppose I want to get this angle. This angle will be tan theta is equal to 1 by -1. So theta is equal to tan inverse -1, which is minus tan inverse 1, you know that, and pi by 4. But you can see this angle is not pi by 4. So what we do is, this is self-explanatory. In order to get this number, I can subtract this angle from pi. This is minus pi by 4 from pi. And when I do that, I write it as pi minus pi by 4, which is 5 pi by 4. So here you see that in this quadrant, I is subtracted from the angle that I obtained. And this is not something, this is not a rocket science. It is self-explanatory. For example, if the complex number is here in this third quadrant, again, remember what is the angle that I'm looking at? I'm looking at angle between the complex number, position vector, which we call it, and this one, right? This angle. So for this angle, remember there's something called positive angle, or there's something called negative angle, depending on the direction that you're taking. So therefore, to get this angle, I am adding minus pi to this alpha, or alpha minus pi, whatever you take it. Similarly, if this is here, I'm interested in this angle, this particular angle. So how do I get this angle? This is a negative angle, or I get this angle. which is 360 minus this. I'm sure this algebra, you know. So whatever theta I get here, you have to add a negative to it, right? So in complex numbers, we have discussed so far, I'm just trying to revise it so that you uh, understand what is important, what is not. We discussed complex number, we discussed the properties of complex number. Not very important. You need to know basics, and that when you add two complex numbers, you get a complex number, or associativity, or closure property, or a into b into c is equal to a into b into c, right? Not very important, but you need to know. What you need to know are two, three things here. One is the additive inverse, right? Multiplicative inverse, and the conjugate. So conjugate for this number is this, and conjugate is used to make uh, to make the denominator of a number into a real one. So please remember, we talked about is in the denominator, never ever have a imaginary number. To make it real, you multiply it with the conjugate. So I hope, I'm sure you would have got some idea about the complex number. These were very basics. In the coming lectures, we will look at some other aspects of it. I'll see you in the next lecture.